Good evening, everyone, and welcome to session 7 of regulatory analytics. So, before we get into the grind of decision tree, let's take a look at what we have covered so far. So, we started off by understanding regulations. What is the meaning of regulations? Right? Why do we need that? And then we spend some time to take a look at applications of AI and ML in regulatory analytics. So, what we are trying to do is we are trying to see how we can use the principles of AI and ML in our domain. Now, obviously, our domain here has something to do with regulations. And as we had discussed, regulations are a very important part of making sure that we don't, not we as in the individual person, but the organizations, the corporates, they don't exploit the world too much, because that's what's happening now. We have, environmental exploitation, workplace exploitation. There are n number of ways in which this exploitation takes place. So what we are trying to do is we are trying to reduce that. We are trying to minimize that. Okay. So what is our aim for today? Today we'll be looking at something we call as a decision tree. A decision tree helps us make decisions like we would. Now, when you're trying to make any important decision in your life, we have to account for so many things. We also want our ML algorithm to be able to account for these things. All right, we want our ML algorithm to behave like human, to at least in a single aspect behave like a human. Obviously, we cannot expect it to always do and make decisions like we do, because our mind is a lot more complex. Our decision making process is a lot more complex. But that might not be the case with machines. So what we are trying to do is we are trying to the best of our ability make the machine have a human-like decision-making system. A human-like decision-making system is very complex. It involves a lot of layers, right? If we have to make any decision in our personal life, we have to think about ourselves. Like, are we making the correct decisions? We have to think about, maybe our friends, our family, our partners. There are so many factors that go into making any decision that, these things do take a lot of time. And there is again, a very high layer of complexity involved in it, right? So similarly, what we are trying to do here today is we are trying to look at non-compliance. Right, we have some compliance requirements. Now, these can be in any sector, or this can be of any kind. All right, what we are trying to do is we are trying to see non-compliance with various regulations. All right, we are trying to understand how organizations are getting picked up. How are they getting fined for not meeting up to the basic compliance? What is the procedure and how we can simplify that procedure using some historical record? So that is the use case we are dealing with here. All right, so we have various different ways. We have civil uh, civil punishment. Now, civil punishment means that you are getting convicted by a civil court. That means the offense you committed was not criminal in nature, but there was some sort of offense that happened. This could be in regards to, maybe your organization was supposed to be using, let's say, for example, 10,000 liters of water per hour, but you ended up using 12,000, which is over your limit. So this is a non-compliance. Okay, so in order to deal with this non-compliance, we have civil punishments. Then we also have criminal punishments. In criminal punishments, the non-compliance was of criminal nature. Like, for example, you were defrauding your shareholders. Now, that is one of the biggest crimes. That is probably the biggest crime that anyone can commit when it comes to financial markets. All right. So, what we are trying to achieve here is we are trying to see how we can use our existing data that will go through. We'll go through our data in detail. We'll try to understand what we are dealing with here. And it's a very, very interesting problem that we have in our hand. All right. But essentially, our goal here is that we have to develop a decision-making algorithm. For a decision-making algorithm, a decision tree is probably one of the best things that we can go for. So first, we'll spend a little bit of time trying to understand what is a decision tree, why do we use it. All right, then we'll go through our use case. We'll try to understand a use case. Okay, so basically here what we are trying to do is we are trying to build a tree-like structure. This tree-like structure starts from the root and it slowly branches out. All right, so that is what we are trying to achieve here. So let's see. So it's a tree-like structure and it contains 3 nodes. The first node is our primary node, that is our root node. Now, any tree we plant, it has to take some sort of root, right? Without it taking that root, we cannot really use it anywhere. It will be weak and it may fall over, right? So similarly, our algorithm will fail if our root is not a strong root. And the model is supposed to be responsible for picking it up. So we'll see how we can help the model pick it up. Now, let's say this is our ground, right? And we plant some roots here. Now that root will grow out into branches. This branch will grow into a leaf. This will grow a leaf. Please excuse my world-class drawing here. So this branch has now leaves. Now branch is a subdivision of our data. All right, we are trying to take some root and we are trying to branch it out to help make better, clearer decisions. And then we have a leaf node. This is the end point. Now, if you look at any tree that you have ever seen in your life, the leaf is the end point. After the leaf, there is no growth on the leaf. The leaf is not sprouting new branches from which, more leaves can form. That is where it all comes to an end. So this is what we call as our endpoint. Okay, so a root node is where our decision-making process begins. Branch node is where that decision-making process is simplified and further divided. And leaf node is where it comes to an end. All right. So the leaf node can also be known as the terminal node. A terminal is something where some value comes to an end. For example, moving completely off the rails here, we have bus terminals. A bus terminal is an endpoint or a start, right? A bus goes around the city in a circle and it comes to a terminal. This terminal is the endpoint of our journey, right? Similarly, a terminal node is where our decision tree stops. This is where the decision tree comes to an end. Okay, so that is what we know as terminal node. Then we have internal node. These are branch nodes. And as we can see in this diagram on the right side, the decision tree is branching out. It started off at the root and it is slowly branching out until it comes to a point where we cannot make any further division. This can be because all possible answers are accounted for, or this could be because we have run out of data to divide. So there can be many number of things that can happen when it comes to a terminal node. Now, let's take a look here. This is a use case we have. All right, here we are trying to use various factors like age, income, student, and credit rating to determine whether a person is going to buy a laptop or not. So here we have taken our student node as the root node. This is where our final decision making is going to happen. Okay, so this is from where our final decision making is going to begin. So first we divide our data according to this column. In this column, we see that we have two possible outputs, whether that person is a student or they are not student. Okay. So we divide our data into two segments. Now this isn't exactly an even split. It doesn't have to be an even split. For example, if we have 100 observations, it doesn't have to be 50-50. Okay. So that is something that we have to keep in mind. It can be any sort of split based on the data split itself, based on that column itself. So first we decide whether that person is a student or not. Then we use income. Using the income, we are dividing the already divided data into smaller portions. All right. Here we are using whatever values we had in student no values and student yes values. Now we have divided our data and now we are subdividing our data. Okay, like this we keep going on until we reach a final decision. So here it took our model a total of 11 decisions. In 11 decisions, it was able to finally account for all possible outcomes that were present in the data using student as the root node. All right. Then here we are going to take income as a root node. Here you can see that the tree architecture is a lot less complex. The decisions are being made at a higher speed than it were when we were taking student into account. All right. So here we have a total of 10 decisions our algorithm has made. So we have gone from 11 to 10. We have improved our model. Now remember, a decision tree algorithm, the less number of rules that are present in the data, in the final outcome, the better it is. Because more rules means more complexity. And we don't want that issue of complexity. Okay. So here we are looking for something called our expected information. That is our entropy. This expected information is how much knowledge are we gaining from the data. Then we are splitting our data into a smaller subsection. All right, and then we are calculating how much information are we getting from that. So we have taken the information from the entire data. Then we are taking information from a subset of the data. We are seeing that if we use this subset, how much information are we gaining? And the more information you gain, the better it is. All right, so this is known as a decision tree algorithm. Here in the outcome, we have two possible outcomes, yes or no. It is a binary classification problem. Now in this binary classification problem, first we try to understand how much information we are gaining in total from our data. We use the same log function we looked at. And we find out that the information gained by splitting this into yes and no is 0.90. Then we use age to calculate how much information we are gaining after we split using age. All right, we find out that we are gaining 0.694 as our information gain. Then using the 0.694 value, we subtract it from the original data set, and then we figure out how much information gain are we having when we use age as the first dividing factor, or age as the root node. And here we end up with only 5 decisions. That means going with a model that is giving you 10 decisions or 11 decisions or 7 decisions or 8 decisions is not good enough, when we can simply use 5 decisions. So this is our entropy. Now let me open up the data set. Just give me a second. All right. So okay, not this one. All right. So here we have a bunch of companies, all right, in various sector of the industry. So we have about 200 unique records for different companies found in violation of some sort of regulation. Then we have the description. This description is telling us in full detail that what did that organization do. So this is a great thing to have in your data as part of your data dictionary, where you're trying to explain why the specific fine is being levied or the specific punishment is being levied. All right. So this is in regards to the data set. So we have the organization name, and then we have the description of the crime being committed by that organization. All right. Then we have a few other important factors. We have their penalty amount. We also have the year in which they were penalized. Then we are looking at any subtraction. Maybe the company proved that their violation committed was not as high as it is otherwise considered. And then we have our final penalty amount. Okay. So maybe there might have been a scenario where somebody might have accidentally double calculated some values. If it is a scenario like that, we try to subtract that information. Okay. So here, then we have the primary offense, what offense was committed. So here you can see we can see that we have a whole different group of primary offenses, from vehicle safety to environment and so on and so forth. All right. We are looking at medical equipment safety violation. All right. We are looking at, again, environment violation. These environmental violations, workplace safety or health violation, product safety violation, motor vehicle safety violations. So we have a whole different group of violations that are being committed by these organizations. So we are trying to understand how to punish these organizations. Excuse me just a second. All right. So here we can see that the offense committed by any specific organization is basically domain agnostic. So then we are taking a look at where that company is stationed. What is the headquarter location? So here we'll find European and Western countries more. Then what type of ownership is it? Is it a private ownership? Is it a public ownership? Is it a hybrid ownership? Here we only have one cooperative ownership. Okay, most of them are publicly traded, which makes a lot of sense because their data will be more easily available than a closed up organization. All right. Then we have the major industry that they are involved with. This is quite self-explanatory. All right. And then we have the civil or criminal punishments. What sort of punishment was handed out to these folks? Was it civil in nature, or was their shortcomings considered as a potential, property to hire or something along those lines? So this is our data set. We have criminal charges. We have civil and criminal charges. We have a whole bunch of civil charges. So basically we are dealing with either one of the civil and criminal charges or one of their many variants. So I'll open up the code and then we'll do some detailed analysis. Just give me another minute. Let the Anaconda open. All right. So let's see. Okay. So this is a very fairly simple algorithm to use, but we'll still go through our, basic pre-processing EDS steps. We'll try to understand what is, going on here. So first we load our data. We take a look at our data set. So we have 199 records of companies being charged with some sort of compilatory regulation. Then we'll check for missing values, and we see that a few columns have missing values. While we are checking for this, we should also check for the near zero variance feature. Let's add that print statement. So here what we see is that most columns have some degree of variance in it, just except for subtraction from penalty. So this means that we should not use this specific column. Similarly, we'll not be using our description column, because file description is a very good tool to use when we are trying to understand the data. It is not very intuitive when we are trying to build an algorithm. So we'll remove description. And we'll remove subtraction from penalty. And then we have to specify the axis as 1, because that is what we are trying to remove here. We are trying to remove some columns. Then we do some imputation for our missing values. And we see that our missing values are now gone. And because they are gone, we can keep moving forward. We'll check for data types. Most of them are object data. We have a couple of string data. Now the advantage of using a decision tree is we don't have to change the data type of the output column. It can stay as a string. All right. So we don't have to do anything about it. So then we'll plot histograms. We'll see these are the columns we are plotting for. So let me reduce the size to something a little more friendly. So this is our first column, that is the company name. How many times is a company name coming up? Then we have the year, the amounts, and who were involved in prosecution of these specific charges. All right, who was responsible for that? Okay, so we have a whole group of organizations, something I should have probably looked at here, that is responsible for identification of these violations. So we have Environmental Protection Agency, Food and Drug, Coast Guard. So a lot of different organizations. This is specifically related to the United States. Okay. Moving back, we can go through this. We'll apply label encoding. So then we take a look at our various columns that are available to us. So we try to find the total number of columns. So we have 3, 3, 9, 9, 1, 10. So we need to go from index position 0 to index position 8. Similarly, we can have same for something like, sorry, why did I put 20 there? So this is our target column, whether the charges were criminal of nature or were they civil of nature, or were they a little bit of this and a little bit of that. So let's build our algorithm. For this data size split, we'll go with 0.42, 0.25, using this 0.25 value, we are splitting our some 200 odd data into 150, 50. Okay. Then we verify the shape, and then we use our ML algorithm. Using this ML algorithm, we can predict our final outcome. So here we have built a decision tree classifier. Okay, we have taken all the input columns into one side, and we have taken all the output columns into another side. Okay, so we'll predict the decision tree, and we'll take a look at the predictions that we have gotten. Now this is also a confusion matrix. This is just a multi-class confusion matrix. Then we check for accuracy. Our accuracy is 0.78. This is our test accuracy. So we are getting around 78% accuracy. While this is not good by any stretch, this is also not very bad. It might not be the worst idea for us to try to perform some sort of hyperparameter tuning on this. That hyperparameter tuning can make the biggest difference in our algorithm. First, we'll check using the training data. So as you can see that it is able to pick up the trend in the union data. But the person is unable to predict the correct decision in the test data. So this is a classic case of overfitting. So in this scenario, we are trying to, minimize that. So we'll also try to plot a decision tree so we can see how it works in real life. So I'll add this figure and we'll increase the figure size. So these are the various decisions that our algorithm has tried to build. I guess we can increase the size a little more so we can read what is going on. So this is our decision tree. So let me just zoom in here. So here we have taken 149 samples. Then we have split them into two categories. 123 going one way or 23 going the other way. So using this, our model is trying to make multiple decisions, although it is crossing over from this plane. Okay, there might be some reason that this is happening. Maybe we just need to, accept it for what it is. Sometimes that is just how things work. All right. So this is our decision tree. Now quickly what we'll try to do is we'll try to use grid search here and see if we can improve on our 78% accuracy. So we'll use sklearn again. Right. Then we'll define some parameters. For example, what is the minimum sample we want to take? What might be the max depth our algorithm should go? So here we have to specify some values. So here minimum sample leaf, we have to specify some value and we'll put it in a list form. For example, 1, 5, 8 and 1, 5, 7 and 9. Then we are looking at max depth. What is the limit with which our algorithm should go for? And then we are trying to figure out how we can extract the maximum features. So here we will be using square root. Now that our grid is defined, we'll try to build our algorithm. So model with grid search. So we'll call our grid search library. We'll say estimator. What are we trying to estimate here? We are trying to estimate our model. Then we'll assign all this parameter grind, the parameter grid. Scoring is done again by accuracy. All right. So here, then for scoring, we'll use accuracy. And then we'll define the number of jobs. That means how many processors we want to run at once. So I will say all. What is the cross validation threshold? 5. So we want it to reflect true. All right. And then we'll say return train score equals to true. So this is our grid search formula. Whoops, got a comma here and here. Do we need to do something else here? Maybe this needs to be separate. I don't think we need to do anything separate here. Let me just quickly figure it out. Positional argument follows keyword argument. Return train score. Maybe if we remove it, okay, what is the problem here exactly? This is the first time I've seen. Oh, I think I know what I made a mistake here with parameter grid. We did not define. Okay. And I cannot spell scoring either. All right. So this is done. So then I will take my grid model. I will fit our training data set. I will fit our outcome here. Max features. Just not been a good day, is it? Making too many mistakes. This has to be within a list like the its compatriot. All right. What is the error here? Max features, max tab, max leaf nodes, minimum samples leaf. Okay, so this has to be samples leaf. All right. So now we have built a grid search model. So what we'll do here is we'll take our best parameters. So our best, this is the best parameters. The maximum depth should be 6, the minimum sample leaf should be 5, and the maximum feature should be square root. So then we'll build a decision tree using the grid model. So I'll build that. Okay, so using this, I'll try to predict on our test data. So basically, we are trying to see if we can improve that 78% accuracy. Test predictors, I think. All right. Okay. So then we'll build our cross table like we built above. So here I'll define it into a name using grid search that we have done this. right? So let's run it. So here we can see that we are getting somewhat similar results. So let's quickly check the accuracy. All right. So we have gotten to 84% accuracy. So this shows that using hyperparameter tuning in a case where you might be seeing overfitting works. All right. So with that, we come to the end of our session 7. So thank you everyone for joining.